Hello once again, grade 11s, and welcome to another video. In the previous video, we looked at the final parts of acids and bases. We looked at titrations, we looked at hydrolysis, we've looked at what else have we looked at? We've looked at it's just hydrolysis, titrations, acids and bases, and ionizations, dissociations, and the exception of ammonia, and so a few other important, just a few important things. Okay, so I just wanted us to look at this particular exam today, past paper that I just want us to go through, just to test our understanding of everything thus far. Okay, I just realized that this particular paper also talks about something that is way out of the scope of acids and bases, which is just percentage purity, and just got some stoichiometry in it. But for the sake of 27 marks, I think we're going to do it, we're just going to have to do it. Unless we could just stop at 7.2.2. Okay. So, by the way, this paper was sourced from a paper from the Eastern Cape, November 2024. Let's just get the precise paper. Okay, there we go. So it is a paper from November 2024, grade 11, and it was paper 2 out of 150. Okay. Now, let's look at this. So this is a typical question 7 on acids and bases, right? And they say to us, carbonic acid, which is this guy, ionizes in water according to the following balanced equation. So carbonic acid ionizes in water according to this balanced equation, right? So they then say to us, define an acid according to the Arrhenius theory. Now remember, in the very first video, we looked at what an acid is according to the Arrhenius theory. What is an acid according to the Arrhenius theory? An acid is a substance. In fact, I'm not gonna write it down. I'm just gonna say it out. Okay, you guys should know this. So an acid, by definition of the Arrhenius theory, is a substance that produces hydronium ions. Remember, hydronium, H3O plus, or H plus, right? It produces hydronium ions or hydrogen ions when dissolved in water. Okay. Keeping in mind that this guy, as well as this guy, basically the same thing, but H3O, okay, yeah, it's just the same thing. I almost said something that just would have just made a lot of people just think twice, But anyway, so that's what we typically have, right? So the carbonic acid ionizes in water. According to this equation, we've defined what an acid is according to the Arrhenius theory. They then say to us, write down the formulae of the two substances that can act as an ampholyte. Ooh, what? Let's start here. What exactly is an ampholyte? Remember, an ampholyte is a substance that can act as both an acid and a base. So an ampholyte can act as both an acid and a base, right? So that's what an ampholyte basically is. So we look at this reaction. Which one is an ampholyte? Which one can act as both an acid as a base and a base? Notice something. There is no such thing as H3CO3 plus. This is a non-existing there is no such thing as this type of ion. I honestly have never seen something like this, and I know you obviously have never seen something like this either. But we do know about the existence of this guy, right? So I noticed something. My carbonic acid can donate a proton, right? And it can donate a proton to the water molecule, so it can be something of this nature. So my carbonic acid can just give a proton to that guy, right? It gives an H plus, and that guy then becomes H3O, and he loses a proton, and then he becomes HCO3 minus, right? If you really looked at the old videos, you would really actually understand what is being done here, right? Okay. Now, what happens? So I have carbonic acid with water. So carbonic acid in this particular case, we can say because carbonic acid donated a proton, what do you know about something like that? According to the Lowry-Bronsted theory, carbonic acid donated a proton. Therefore, we can say that H2CO3 having donated a proton is our acid, right? And what received the proton? Water. Therefore, we can say that water is our what? Yes, a base. Cool. Now they say that they want the formulae of the two substances that can act as an ampholyte. So what is an ampholyte? A substance that can act as both an acid and a base. Now notice something. We've looked at ampholytes in one of the videos we had before, right? And we've said that HCO3 is one of the ampholytes that we know. Why? Because when HCO3 minus, remember, it can act as both an acid and a base. So when it acts as an acid, it loses a proton. When it loses a proton, we expect to see something like CO3 to minus. That's when it has lost a proton. That is when this guy acts as an acid. But what happens when he acts as a base? So when carbonic acid acts as a base, so when, sorry, not carbonic acid, but the hydrogen carbonate ion. So when this guy acts as a base, he gets a proton. Remember, he receives a proton and he becomes H2CO3. So for starters, this guy can be both an acid and a base. Therefore, we have our first formula of our ampholyte. So we have, for starters, our ampholyte will then be HCO3 minus, and the second one would be, now let's see which one the second one would be. So the second one could be, okay, so let's just see. So here's what happens. So with the second one, what do we have? Let's look at water. What happens when water acts as a base? When water is a base, it receives a proton. Remember, it receives a proton. What does it become? H3O plus. When it receives a proton, it becomes H3O plus. But what happens when water loses a proton? Can it lose a proton? Yes. When water loses a proton, water then forms OH minus. So that is when water is an acid. So you notice something. When water is an acid, it forms OH minus. When it's a base, it forms H3O plus. Therefore, our two ampholytes would then be carbonic acid, HCO3 minus, as well as water. There we have it. So those are the two answers that we have there. Okay, cool. They then say to us, write down the formulae of the two acids. Okay, I'm just gonna say, okay, I'm just gonna write these at the top because now it just becomes a mess. Okay, so we have ampholyte number 1, which is HCO3 minus, as well as water. So, 7.1.3 wants the formulae of two acids from the reaction. So two acids from the reaction, what are acids? Proton acceptors. Sorry, proton donors. So we already identified this guy as our first acid, but which one is also our acid? Think about it. In the reactant part, water cannot be an acid. Because if water is an acid, it has to give a proton to this guy. And if I give a proton to this guy, I form H3CO3 plus, which is a non-existing ion. I've never seen an ion like that. So we then know that water cannot be an acid in this case. Then what happens, which one would then be our second acid? We then identify H2CO3 as our first acid, and we say that this guy could also be an acid, meaning this guy could donate a proton. So our first acid would be H2CO3 as well as H3O plus. But if you think about it, this guy can also be an acid. I mean, it's an ampholyte. So if I can take HCO3 minus and I make it an acid, that means it loses a proton and it forms CO3 2 minus. So you could also have this guy as your answer. I think you would be marked correctly, right? So yeah, so on my side, these are the two answers I have. It's the carbonic acid as well as the hydronium ions. You could have the carbonic acid as well as the hydrogen carbonate ion, or you could have the hydrogen carbonate ion as well as the hydronium ion. It really didn't, I don't think you'd be wrong in that case. Okay, now what do we look at? 7.1.4 says the balanced equation between carbonic acid and sodium hydroxide. Wait, what? Oh, sorry. Write down. I got a little confused there. So they say write down the balanced equation between carbonic acid and sodium hydroxide. So we now know that carbonic acid is H2CO3 and we reacted with sodium hydroxide. So what would our balanced reaction be? Remember, first with second, second with first. So H2 is first, it goes with the second part here. So it has, we know that, I mean, if you look at it, you would have an acid and a metal hydroxide, right? Sodium hydroxide is a base, but it's also a metal hydroxide, hydroxide, you know? So remember, I think that's from the proteolytic reactions or the acid-base reactions video. We had this as the third reaction, right? So metal and metal. No, it was actually the second reaction. And we know that we need to form water. So that we need to form water and some salt. So what is our salt in this particular case? Our salt would then be the formation of, remember, second with first, first with second. Oh, second with last. So sorry, first with the last, second with first. Yeah. So I would have my first in this particular case as CO3, and so CO3 is my second, and this guy is my first. These two then give me sodium carbonate. Yeah. Now you should know that sodium carbonate is actually written in that way because sodium has a charge of a +1, the carbonate ion has a charge of 2 minus, and from that and your knowledge you've acquired in grade 10, you should know that it's fine. So let's see if it's balanced. Okay. So how do we know if it's balanced? We will see. So how many hydrogens on the right? On the left, I have 2 plus 1, that's 3, and on the right, I have 2. So I know my hydrogens here would be 2, and here my hydrogens would be 1, right? And then on this side, I have my hydrogens being equal to 2. And then my carbons are fine. I have 1 carbon here, 1 carbon there. I have 3 oxygens plus 1 that gives me 4 oxygens. I have 3 oxygens plus 1 that gives me 4 oxygens, so that's fine. And I have my Na2, so I have 2 Na, right? So notice something. Balancing might be a problem here because I don't have enough space. Let me see if I can just get some space. Okay, just gonna have to thug it out. Okay, so I have this guy here. So now remember, this now affects my number of hydrogens, and so I have hydrogen, carbon, oxygen, and sodium, right? So this is what I have. And on this side, I also have my hydrogen, my carbon, my oxygen, and my sodium. So my hydrogen in this case is 2 and, well, 2. And in this case, it's just 2. And my carbons is 1, and in this case, it's 1. My oxygens are 3 and 2, okay? Is that 2? Yes. So it's 3 and 2. And my sodiums are 2, and here my sodiums are 2. What are my hydrogens on this side? It's 3 and, well, 1. Okay, so now we need to start balancing. Now notice something. I can just multiply this. I can just put my stoichiometric coefficient 2 here because I multiply that guy. I think I should use different colors for this one. So I multiply, no, we've had that, this is black. I multiply that guy by 2 and I get 4. And you notice that 2 plus 2 gives me 4. So my hydrogens are balanced. Cool. Are my carbons balanced? Yes, my carbons are still okay. Are my oxygens balanced? Well, I have 3 and 2, that gives me 5, and I have 3 and 1, that gives me 4. But now notice that this one here was multiplied by 2, which gives me 2, and that gives me 3 plus 2, which then gives me 5. Aha. And this also gives me 5. And then these are balanced. Okay, so that is my balanced equation, right? So we have officially balanced our equation. And please, guys, do make sure that in the exam, just if it means you have to do what I did here, then do it. Just make sure that you do it and consider the time as well, because we need to make sure that we finish the entire paper. So that is our balanced equation. So it's H2CO3 plus 2 NaOH to give us Na2CO3 plus 2 water molecules. Okay, so that is our balanced equation. 3 marks. So you got yourself a 32 marks for the definition. So it's just, you got yourself something over there, you got yourself something over there, and 3 marks over there. Now, they then say to me, 2 grams of sodium hydroxide is dissolved in water to make 100 cubic centimeter solution. This is a part where I like, you need to make sure that you collect your data. So what is our data? Our data in this case is that we have the volume of sodium hydroxide. We have the volume of, sorry, not the volume, but the mass. We also have the mass of sodium hydroxide as, okay, we have this as 100 cubic centimeters, and we have this as 2 grams. So how do I move? Now, what's my goal? I need to calculate first the concentration of sodium hydroxide. Can I do that? Yes. I can use the equation C equals 2m over mv. Or you could start by saying n equals to m over m, and then getting a number of moles, and then taking a number of moles and substituting it into n, c equals to n over v. You know, anyway, it's just correct. You know, it's just as correct. But it's a bit tedious on my side, so I just prefer to use this equation, right? But whatever works for you, please use it. Okay, so concentration is, what is the mass? The mass is 2 grams. And what is the molar mass of sodium hydroxide? Well, if you consult your periodic table, you should find that the molar mass of sodium hydroxide is exactly 40. Should give you a 40. And the volume we had was 100 cubic centimeters. So I know that I need to divide that by 1,000 in order for me to get my cubic decimeters. And that gives me that, and that. That gives me 0.1 cubic decimeters. So that's going to be 0.1. Okay. Okay, so my final answer of the concentration would be 40 times 0.1. And that should give me an answer of my concentration as 0.5 moles per cubic decimeters. Now, if you had to use the equation n equals to m over m, and then take this and then use n equals to c over c equals to n over v, you would get to the same answer, you know. But like I said, it would be a bit tedious. But if it works for you, then you can stick to it. So concentration in this case was so the concentration we have here is 0.5 moles per cubic decimeters. Okay, so that is our concentration. Okay, right there. Cool. Okay. Now the next question says, calculate the pH of sodium hydroxide. Okay. Now think about it. So, okay, when we calculate the pH, we have these two equations. So there's an equation to calculate the pH and an equation to calculate the pOH. So pH is negative. Sorry, just gonna write it up here. So you should just note this. So the equation of calculating pH is pH equals to the negative log of the concentration of the hydronium ion, right? So pH is the negative log of the concentration of the hydronium ion. So you would eventually just need to get the concentration of the hydronium ion, this guy, substitute it in there. So you get negative log, say the concentration you've got was 0.5, and then you get your pH. Okay. And to calculate what we call the pOH, you would then have something almost similar. So it's pOH equals to the negative log of the hydroxide ion. So the negative log of the hydroxide ion. So you'd have this guy right there, right? So it's a negative log of the hydroxide ion. That's my pOH. Another thing you need to know is that pH plus pOH is 14. Now this is because the pH scale ranges from 0 to 14, right? So if I have the sum of the pH and the pOH greater than 14, I just break the pH scale. At that point, I really don't know what it is, right? So I know that pH measures this, so pH would be using the hydronium ion, meaning it would be somewhat for the acidic part. So it would be for the first part from 0 to 7, right? From 0 to 7. And then from here, we would have something like that. So the pH would be from 7 to 14. So if I add these two, this portion here with this portion here, I should then make my entire scale of 14. Right? Okay, that's very important. So that's just, please note that down. Okay, so I've looked at the pH as well as the pOH. Okay, so these are the respective equations we're going to use. Another thing, I just want you guys to know something. If I say that pH is negative log of the hydronium ion and pOH is a negative log of the hydroxide ions, how then do we get those concentrations? Well, we do have the concentration of sodium hydroxide. Now, I want you to note something very, very important. We know that we talk about stoichiometric ratios, right? And when we refer to that, we are referring to the number of moles. But when we want to calculate the pH, we look at how a certain base dissociates or a certain acid ionizes. So in this particular case, we would say, with the pH, we look at the stoichiometric ratios. Remember with this one, we look at the stoichiometric ratio, we talk about moles of different substances, right, that are reacting with each other. But in this case, we look at the stoichiometric ratio, we look at the concentration. And in this case, we're not looking at substances, we're looking at a certain substance, may it be an acid or a base, with its respective ions, right? So in this particular case, I'm saying, just look at something. So in this case, I'm basically saying that I would have something like this. So just remove all of this. So if I had to calculate the pH, you'd notice in the reaction, I mean, I'm given sodium hydroxide and I'm not given any acid. So there is no way that I could just come up with the concentration of the H3O plus, right? But I can think smart about it. In what way? So I can say, thinking smart about it would basically mean that I would have something like this. So H3O plus would then mean that I would easily determine my pH because of the equation, but I don't have the concentration of H3O plus. What I do have is that I know that when sodium hydroxide ionizes, what does it form? When sodium hydroxide ionizes, it forms OH minus plus Na plus. And I know already I can easily get this guy right here and then I can use my POH equation. Now, let's see. So I have that, and I can have, okay, my POH equation would be used, and then from there I can use the fact that POH plus pH gives me 14. Therefore, pH would then be the difference of 14 and the POH, right? So that's our plan of attack, basically. So, remember, I said that the stoichiometric ratio is when we want to determine the pH. Well, we look at the sodium, we look at some substance with its ions. So we're looking at the ratio of sodium hydroxide and its particular concentration, right? So I then say there's 1 mole here. So there's 1 mole there and 1 mole there, meaning that the concentration of NaOH is equal to the concentration of OH, right? So that's what I'm basically saying. Remember, if it was with the number of moles, then you would say that the number of moles of sodium hydroxide equals to the number of moles of the OH minus. But in this case, we're looking at concentration. So I then know that from that, I can then conclude that the concentration of OH minus equals to the concentration of sodium hydroxide, which in this case was 0.5 moles per cubic decimeters. Cool. Now that we've gotten that, we can then use our POH equation. So our equation is POH equals to negative log of the hydroxide ion, and that's negative log of 0.5. And according to my calculator, that gives me 0.3. 0.30. So that's what it gives me, right? So that's my pH. My pH gives me, sorry, that's my POH. So how do I determine my pH? Remember, POH plus pH is 14. Therefore, my pH will be 14 minus 0.5. And my pH would then be 14 minus 0.5. And according to my calculator, that gives me 13 point, sorry, not 0.5, 0.30. So sorry. So minus 0. That gives me 0.30, and that gives me an answer of 13.70. Now, if you think about it, sodium hydroxide is a strong base, right? So if sodium hydroxide is a strong base, then I'm expecting its pH to be greatly just bigger than 7 and somewhat very close to 14, because the closer it is to 14, the stronger it is. And notice something, 13.70 is not really that far from 14, you know? So you would basically confirm that your pH is correct, because now you know that the pH for starters is greater than 7, meaning it's basic, and it's closer to 14, meaning it's a strong base, and you actually do know that sodium hydroxide is, in fact, a strong base. Okay, cool. I think that covers the question. So what is our pH? Oh, I removed it, but I think I remember it. It is, what is our pH? Oh, 13.07. Okay, I'm just gonna write it down here. So our pH is exactly 13.07. Okay, so that is our pH. Cool. So what then will I have? Sorry, okay, I'm just gonna remove this. And then the question continues. They then say 5 grams of impure magnesium carbonate is added to 9.033 times 10 raised to 22 molecules of hydrochloric acid. The balanced equation for the reaction is given below, and they say the reaction is allowed to proceed until all the pure magnesium carbonate completely reacts. The excess hydrochloric acid, if hydrochloric acid is in excess, we then know that magnesium carbonate is limiting, right? So the excess hydrochloric acid is then neutralized by adding 55 cubic centimeters of the sodium hydroxide solution of concentration 0.8 moles per cubic decimeters. And the balanced equation for the neutralization reaction is HCl plus NaOH to give us, so salt and water. Okay, sorry, it just made me think that's a negative. That's water minus and just crazy. So for starters, we need our data. What do we have? We have the mass of magnesium carbonate, the mass of magnesium carbonate, and that gives me 5 grams, right? But they say something about it. They say it's not just any mass, but it's the impure mass. I mean, if I see something like this, I know definitely I'll be asked to calculate the percentage purity. And yeah, that's, aha, there we go. You see, you are actually asked to calculate the percentage purity. Right, and remember, what is the equation for percentage purity? Remember that percentage purity is equal to the mass of the pure substance over the mass of the impure substance times 100, right? And you always leave your mass of the impure substance at the end because you're only going to use it once you start determining a percentage purity. So you mize this guy. This guy just mize him. You mize him for some time. You're just gonna mize him and you're gonna see him at the end, right? So during your calculations, you're just gonna let him be. Just leave him alone. Don't look at him, you know? Okay. So we have our mass, and what else do we have? So we have the mass, what else do they give us? And they give us the number of molecules. They then give us the number of molecules, which is exactly 9.033 times 10 raised to 0.033 times 10 raised to 22. Now you're probably wondering why I'm using the big M, right? Remember, these are molecules, right? And that takes you back to the equation in grade 11 that says N equals to big N over NA, with NA being Avogadro's number, right? So that's why. And we knew that this guy represented the number of molecules or atoms or particles, etc., right? Okay, so that's how I actually knew that. Okay, cool. What else did they give us? They didn't give us and then they also give us excess hydrochloric acid, the volume of sodium hydroxide. They say that the volume of sodium hydroxide is 55 divided by 1,000. That should give me 0.055. Okay, so it's 55 divided by 1,000, and okay, so that's my cubic decimeter volume. Cool. And then what else do they give me for sodium hydroxide? They give me the concentration. So they give me the concentration of sodium hydroxide, and that gives me 0.8 molars, 0.8 moles per cubic decimeters. Okay, coolios. Now, what then can I do? Now I can use my data to solve the following questions. For starters, they say to me, calculate the number of moles of hydrochloric acid. Now remember, go back to the equation, N equals to N over Na. Remember that this was the number of moles, this was the number of atoms, molecules, and particles, and then this guy was Avogadro's number. And according to Avogadro's number, I'm not sure if they give it to you down there. I think it should be 6.02 times 10 to the 23, but let me just make sure. They should give it here. Yes, right there. 6.2 times 10 to the 23. Okay, good. So now we have our number, our NA, and we also have our big N. So if I substitute this, I can have, remember from our data, remember the importance of the data, very important. So it's 9.033 times 10 raised to 12 divided by 6.02 times 10 raised to 23. And that should give me an answer of exactly, please do confirm on your side, but I get 0.15. moles. But what are these moles for? These moles are the moles of HCl. Okay. We've answered the first question, so I'm just going to remove these because now it just becomes an entire mess. So we've answered the first question, and hopefully we are all confident with the answer. Okay. We then look at the question, 0.3.2, they say calculate the percentage purity of magnesium carbonate, and that is a big 8 marks that we cannot afford to lose. Okay, so we need to determine the percentage purity. Oh, and I just start by using the 5 grams as my initial mass, and that's just the impure mass. So, oh, don't do it. It doesn't matter. Okay, so I would have my 0.15 moles of HCl. Okay. Now, for starters, I want the percentage purity. So what is our plan of attack? So think about it. You should always have a plan of attack. So the thing about chemistry is that you always use what you're given to get what you want, right? So what are we given? We're given the 5 grams of impure substance. No, do not start with it. Remember, we'll leave it for the end because it is the impure substance. You only use it when you want to determine your percentage purity at the end, right? So what do we have? So we have the volume and the concentration of sodium hydroxide, right? Yeah, we can do something about that. What can we do? So I have the volume and the concentration. Think about it. Yes, I can get the mass. So C equals to N over V. I can get the number of moles. Sorry, not the mass. So my number of moles would be what's the number of moles? So it's C times V, which would be the concentration was, according to my data, 0.8. So that's 0.8, and my volume would be 0.055. That would give me 0.8 times 0.055, and that gives me an answer of 0.044 moles. So those are the number of moles that I have for sodium hydroxide. Now, what do we actually want? Remember, percentage purity is the mass of the pure substance over the mass of the impure substance. Now, what you need to know is that in a reaction, it is the pure substance that actually reacts, right? So it's like in this particular case, we are only reacting the pure substance. So that's what we want to get. That is why we use everything of sodium hydroxide to get the mass of the pure substance, because it is the pure substance that actually reacts. So it's the mass of the pure substance of the mass of the impure substance times 100. So what then is my mass of the pure substance is what I actually want, right? So I want to eventually get my mass. So I want this guy. So I know that I can get him by determining the number of moles and then getting the molar mass. But how do I get the number of moles of hydrochloric acid? Now think about it. Think about it for a minute. 10, 5, 4, 3, 2, 1. Aha, you got it. You need to use the stoichiometric ratios. Yes, the stoichiometric ratios. The stoichiometric ratios. So if you look at the stoichiometric ratios, we notice that this is at a ratio of 1:1. Therefore, I can conclude that the number of moles of HCl, in fact, before I can just say that, you need to say that they are at a ratio of 1:1. Therefore, the number of moles of HCl should be equivalent to the number of moles of sodium hydroxide, which therefore we can say that the number of moles of HCl is 0.044 moles. Aha. Fairly easy, very nice, you know? Okay. So what next? Okay, now we've determined the number of moles, and what else do we need? So we've determined the number of moles. Do we need anything? Yes, now we can get our mass. So we can say N equals to M over M, and that gives me my mass equals to the product of N and my molar mass. And that should be, okay, I'm just going to erase this because now I'm just running out of space. It's just a thing I hate about writing on the question paper. Okay, my space is so limited. Okay, So from here, I can then take this and just bring it down here. Okay. So I have M equals to the number of moles to 0.044 times my molar mass, which is what's my molar mass of sodium hydroxide? 40. So it's 40. And let's see, so I get 40 times 0.044. That should give me an answer of 1.76 grams. These are the grams that are pure. Okay. Now, another thing, a very important thing, you know that when you're determining your percentage purity, you are actually determining a percentage. And never in a million years will a percentage be greater than 100, especially with the restrictions in the grade 11 syllabus. You know, it's you cannot get a percentage that's greater than 100. Unless in other subjects it's possible. Well, it would obviously depend on the type of topic you're doing, but in physics and in maths, you should never get a percentage greater than 100. So we then know that our percentage purity would be the mass of the pure substance divided by the mass of the impure substance times 100, right? And you then now know that if I substitute, oh yeah, in fact, with the point I was trying to make, I just digressed from that, I don't know how. But with the fact that I made that you can never get your percentage of 100 is that it is impossible for you to get your MOPS greater than your MOIS, meaning you can't have your denominator greater than your numerator. Sorry, you can't have your numerator greater than your denominator because it would lead in a percentage greater than 100. So think about it. Let's say we had 5 over, so let's just take the 5 grams and we divide it by 1.76. We multiply that by 100. On my side, I get a percentage of 284%, which is bonkers. Okay. Now, I then say, so my mass of, so it's very important that if you, just to check, perhaps in the exam whether you're correct or not, just make sure that you check your mass. Your pure mass must be less than your mass of the impure substance, right? So now I can substitute 1.76 and divide by 5, multiply by 100. I get my percentage purity as 1.76 over 5 times 100, and I get that as 35.2%. Right? So that's a 35.2%. That's the percentage purity that I actually get. Okay, but actually notice something. There's a blunder. There's just a problem in what we have actually done here. Because now percentage is very low. Okay, now I see. So this entire thing was just a mistake. So I'm just going to remove that. I'm so sorry. I want us to look at something. Just think about it. Just made a very huge mistake here. Now I want you to think of something. Remember, the statement actually said something that we need to consider. What the statement said to us was that something was in excess and something was limiting, right? So you then need to know what was in excess and what was limiting. They say that magnesium carbonate was limiting and hydrochloric acid was in excess. So the number of moles in hydrochloric acid that reacted with sodium hydroxide were the number of moles that were in excess. What we want is the number, percentage purity. Oh, you see what I mean? So we wanted the percentage purity of magnesium carbonate, not of hydrochloric acid, right? So look at it. So we are saying that we have excess hydrochloric acid, meaning that is used to react with NaOH. So the number of moles of HCl that we got was 0.044 moles. But remember, what reacted with sodium hydroxide? It was excess hydrochloric acid. So excess hydrochloric acid has that particular number of moles. Now we need to get the number of moles that actually reacted with magnesium carbonate. Remember, those are the number of moles original. So we have the original number of moles. We have the number of moles that were in excess, right? So we have the original number of moles and we have the number of moles in excess, right? So we need to get the number of moles that actually reacted with magnesium carbonate. So now we need to look at this and we need to say, remember, the initial number of moles or the original number of moles of hydrochloric acid was 0.15, but the number of moles that reacted with sodium hydroxide was 0.044, meaning there is some number of moles from the original, there is some number of moles that reacted with magnesium carbonate, right? So it's a very important thing to consider. Okay, so what do we do? How do we get then the number of moles that actually reacted with magnesium carbonate? We then say that the number of moles that reacted with magnesium carbonate should be the number of moles initial minus the number of moles that were in excess. Now think about it. The number of moles in excess, the initial number of moles, the total is equal to what reacted and what was left, right? So that is why I would say that the number of moles initial would be 0.15 minus 0.044, which are in excess. And I get an answer of 0.15 minus 0.044 of 0.106 moles. So these are the number of moles that actually reacted with magnesium carbonate. Now, from here, we can then determine our molar ratio of magnesium carbonate and HCl. We then say, for every 1 mole of magnesium carbonate, I react 2 moles of HCl. Therefore, I know that the number of moles of magnesium carbonate, you can also test it yourself, should be 2 times 0.106, so that gives me 2 times 0.106, and that gives me an answer of 0. Wait, hold on, sorry, 0. Okay, hold on, just so for every 1 mole of magnesium carbonate, I have 2 moles of HCl, so it's 1 is to 2. I don't have that, and I have 0.106, and I know that the number of moles of, you can also try it, of magnesium carbonate would be 0.106 divided by 2, and that gives me 0.053, yes, 0.053 moles of magnesium carbonate. So now that we have the moles of magnesium carbonate, we can use those moles to determine, yes, our mass of magnesium carbonate. Can then say, so it's going to be the mass of magnesium carbonate. What do we have? So the number of moles equals to m over m, and my mass should be magnesium is 24, so let's make magnesium, yes, 24, magnesium is something different, plus 12 plus 16 times 3, that should give me 4.452 grams. So that is the mass that I actually get, right? So this is the mass that I get for magnesium carbonate. So how do we then get the percentage purity? Now notice something. This guy, the pure mass, right? It's just a very important thing. The pure mass, this guy, is less than the impure mass, this guy. So we would actually expect for our answer to actually work, right? So now we're going to take the 4.452, right? Yes, 4.452 divided by 5 times 100, and I get my answer as 89.04%. That is then my percentage purity of magnesium carbonate. Okay, so that was a very, very enjoyable question, and you have gotten yourself full 27 marks. But we also need to consider something, just a mistake that I made, just a very stupid mistake. It's very important that you read your statement very carefully, which I did not do that, but you should do that, right? They did tell you that hydrochloric acid that was in excess reacted with this. So that whatever the number of moles you get of hydrochloric acid here in this reaction will be the ones in excess. You can then get the ones that actually reacted with this guy by taking the original, which was 0.5, minus what reacted here, and you would then get the ones that actually reacted with magnesium carbonate, and then you would be able to get your percentage purity. Okay, then whatever comes here, redox reactions, we're going to look at that in a later stage. Okay, but anyway, I think that brings me to the end of this question and the end of this video. Thank you for watching.